You take the regular part of this equation, you get that equation over there. And I'm going to write this addition theorem differently, and you can see it as a change of coordinate system. Okay? So because of that, these are also called translation operators. And this is alpha translation operator, beta translation operator. What the translation operator does for you is to just change the coordinate system of the wave. You change the coordinate system of the wave from this coordinate system to that coordinate system. Okay? So, in order to make this more suggestive, I would rewrite this as that an addition theorem with a coordinate system rho sub j is one where rho sub j is a vector emanating from an origin oj. Okay? And that can be written as phi t rho sub I dot with beta ij. And rho sub I is something that, a vector that is emanating from I can think of it as that way. What I have done is actually a way of changing coordinate system. This wave seems to be emanating from OJ. This wave is emanating from OI. Okay? And this is the top part of the addition theorem. And then the bottom part of the addition theorem can be just rho I, and then say alpha ij. So you can think of this as a translator that changes from coordinate system j to coordinate system I. This is also a translator, translation operator that changes from this coordinate system. And then it has to be valid only when rho I is larger than this distance. Okay, if rho I, this distance here is rho I minus rho j. Okay, that distance there is rho I minus rho j. And that if rho I is larger than that distance, okay, this is originally the source that emanates from this point, is what the left-hand side means. And if I change it to a new coordinate system that's changing from this coordinate system to that coordinate system, it's like changing from this coordinate system to that coordinate system, my rho sub I must be outside the circle. Okay, there's a circle here. The same circle as I had drawn just now. Okay, that is a circle. If my rho sub I is larger than that circle, it's the same as I'm outside that circle over there. Okay, so this is the same as this thing has to be larger than rho I minus rho j. Okay, the other circle is the same as rho I less than rho I minus rho j. So this is just another way of writing the coordinate system, writing the translators so that they have physical meaning of changing coordinate system from j to I and so on. Okay, can everybody see that? Okay, outside here, you have only outgoing wave. Inside there, you have standing wave. That is when you change from this coordinate system to that. It's the same. Okay? Any questions? Any problem following it? And then I can write the same for this one also, which I would not write. Okay? Now, I can use this to do fancy translations of coordinate systems of a very complicated vector wave function. Okay, let me do a very fancy translation. Okay. So if I had this, then let me write this again, but it's not very nice to do this. But let me write this addition theorem in a different way, so that okay, you have a vector rho ji. This means that I have a vector that goes from coordinate system I to coordinate system j, or maybe a point I to point j. I will call this rho ji. Okay, I read this index from left to right. Okay, let me call that to be the vector. Then you can see that this rho ji is the same as another vector rho jl. Okay, let me call this OL. So that picture is the same as that picture over there. Rho jl is a vector pointing from OL to OJ. I can rewrite this from the addition theorem to be equal to psi t using this top part of the addition theorem, rho jl, and then beta li. Okay? So I call this beta that changes the coordinate system from origin OI to origin OL, beta IL. Okay, beta IL. And then this vector I just rename it beta JL. So it's the same picture as that over there. So that allows me to do the translation. A wave that is emanating from here, okay, as long as I'm outside this circle. If I'm outside this circle with that circle over there, it's not a very good drawing, but you know what I mean. If I'm outside that circle, then I can use this translator. If my observation point K is far enough outside the circle, then I can use this translator. Okay? And then I can further change coordinate system and say that this is actually the same as let me write it down here. The same as the regular part of a wave function with a new coordinate system L prime. Okay, this is JL prime now. And then dotted with a new translator that changes a Hankel wave into a Bessel wave. So it has to be this kind of a translator or that kind of a translator. I just want to change this into a Bessel wave. Okay. So I will replace this with alpha L prime L. Okay, and then put the original beta over there. So I can do one more translation of this nature. Let me draw a better picture over here. I have OI, I have OL, which is over here. Okay, and then outside this circle, I have a circle of dichotomy. Okay, if I'm outside this circle over here, I can do the first translation. I can do the first translation and change the wave to be as if it's coming from here. Instead of the wave coming from there, okay, let me draw the picture better so that I'm further out. I'm even further out. Okay. Originally, the wave was emanating from here. Okay. After the first translation, the wave seems to be emanating from OL. Okay. It's what the first translation did. It seems to be emanating from a different origin now. And then I'm going to do one more translation. The translation is to make the wave seems to be a standing wave of our new origin. And that standing wave is valid if, I guess, let me see, those waves are coming in like that. And these are all Hankel waves that are coming out from here. Okay? And then this translation from here would be valid, and they are all standing wave about a new origin, say OL prime. Okay, OL prime out there. And this will be standing wave about this new origin system. This is what that means. Okay.
How did you get OL prime?
What is that?
How did we place OL prime?
So this vector here will be rho J L prime. Okay. This first vector will be rho J I. The second vector here will be rho J L. The third vector will be rho J L prime.
Is there a constraint on how far the L prime can be from L? Or I mean from
Yeah, it seems that when you translate from here to here, you're translating an outgoing wave to become a standing wave about this point. So the constraint on the second translation is this circle. But the constraint on the first translation is outside that circle. So the overlap region is that you have to be inside this circle. Okay, the overlap of the two zones. Okay, only inside that circle can you make that translation. Because the translation, first translation has to be outside this circle, second translation has to be inside that other circle that I drew. Okay, this other big circle, because it goes from here to here, and then overlap region is that circle. So this is valid as long as I'm inside this circle. Okay. Yes?
OL prime has to be outside that that circle that's formed by the radius of the bottom two origins.
Right, right. It has to be outside the circle.
Yeah.
Because outside the circle can only you have an outgoing wave. The first translation has to be outside that circle. Okay? Because the outside the circle, you can do each of these translations to become a standing wave. So the validity region is the overlap of the two regions. Okay? So, now I'm going to do the last translation. Last translation is to make this standing wave to become like standing wave about this point. Okay, about that point, yes.
Actually, can I reiterate that last point?
Okay, go ahead.
So this guy is supposed to mimic the field of this guy.
Right.
But that's only true out here, outside this circle.
Outside this circle. Outside this circle.
And this guy is supposed to mimic the field of this guy that mimics the field of this guy.
Right.
So if you expand this in the wrong place, you're still mimicking the field of this guy, but remember this guy is wrong. If you expand this here instead of here, you're still mimicking this guy correctly, but you're mimicking this guy incorrectly because this guy does not mimic this guy correctly in here.
Right. You're violating the first condition. That's right. Okay. You're violating the first translation condition. So this formula is only valid in this circle. Okay. Very good. Okay. And then I'm going to do one last translation, saying that I'm going to translate this standing wave. Instead of standing wave about this origin, there will be standing wave about that origin. I'm going to use a regular part of this, which is a regular equivalent part of this. So if there's a standing wave about that origin, okay, then it is right at the observation point. I make the observation point a new origin. And in this new translation, it will become an origin. And then the last translation is the regular to regular translation. Regular to regular translation involves a beta matrix. So it becomes a beta J L prime dot alpha L prime L dot beta Li. Okay? So that allows me to factorize a Green's function, factorize a wave into product of three matrices. Product of three matrices using translation operator, which follows from addition theorem in quantum mechanics. Okay. So what I have effectively shown is the fact that if I start out with this function over here, okay, it can be replaced with this function. But what is this function? These are all the Bessel functions evaluated at the origin, right? These are all the Bessel functions, remember? This is a stack of Bessel functions. What is the value of Bessel function at the origin? 0, except for one term, when m is equal to 0. So every element of this vector will be 0 except for one that corresponds to m is equal to 0. Okay? So what I have finally is that this has only one non-zero element multiplied by a vector, multiplied by a matrix. Finally, this becomes a column vector as well. I will get just a column vector if I multiply these two out. I will get this matrix still there. I'll get this matrix still there. So if I translate a multipole correctly from one origin to another origin, I get this final relationship. Okay? What happens if I have started out with a monopole on the left-hand side? Instead of using a common vector that has non-zero elements everywhere, I only keep one term on the left-hand side, which is the monopole. Okay, which is this term over here. Rho ji, right? If I only keep this term on the left-hand side, if I only keep one term on the left-hand side, this would be just one number on the left-hand side. And then this would have been converted to a column vector. I only need to take one column of this matrix system if this is a monopole, if it's a scalar number. So if I have started out with a monopole, okay, this would have become a vector itself also. Okay, what it says is that if I started out with a monopole, then the factorization using translation operator becomes just this. I would have also started out with a column vector. This would have become just a column vector. Okay, and this successfully allowed me to factorize this Green function into product of three terms. Okay, can you follow that? And the factorization is using translation theorem that follows from the addition theorem. Okay, I'll let you digest this a little bit. Let's take a coffee break. We can let you digest this a little bit, and we can come back to see how we can use this to speed up computation. The factorization of the Green's function. This is essentially the Green's function in 2D. And doing the same thing in 3D, you can also come up with the factorization of the Green's function. You start with a general multipole, but you restrict yourself to a monopole. You translate to an arbitrary location, but if it is you make this to be the origin, only the monopole term survives. The column vector becomes a column vector, and you have that factorization. Okay, I'll let you digest this a little bit. Come back to it.